The last part of this chapter we're going to talk about is the acid-base properties of salts, how the acid structure affects acidity, as well as the definition of a Lewis acid and base. Oftentimes lately we've been really thinking about what happens when an acid or a base are added to water. But as you know, when we have an acid, let's just call it HA, and it reacts with water, it produces hydrogen ion, so hydronium, plus the conjugate base. So this conjugate base is some kind of anion, right? So when we have hydrochloric acid, the conjugate base is chloride ion. When we have something like acetic acid, the conjugate base, the anion is acetate. So those compounds can now be, they could be included with other compounds or with other like cations. So let's say I had something like sodium plus my A. So that could be like sodium chloride or sodium acetate, for example. And I put that in water. What's going to happen? So what we do actually is, I'm hoping you've realized that when an ionic compound that has a group 1 metal, so like sodium, is added to water, that really just separates and it doesn't react with the water. It just floats around and is hydrated. Now this anion here, which will have a negative charge, now it can act like a base. So it's going to pick up a hydrogen from the water and become HA, and then we're going to be left with hydroxide. So now we're going to be thinking about, if I have a conjugate base that is on its own added to water, what's going to happen to the solution? Or if I have a conjugate acid, think like ammonium, right? If that's mixed with something like chloride, what's going to happen when it's dissolved in water? And so when some ions react with water, they create hydrogen or hydroxide. So that is called hydrolysis. Hydro meaning water and lysis meaning breaking. So breaking up water. So to think about whether a certain ionic compound or salt is acidic or basic, we want to look at the cation and the anion separately to see what they will do, if anything, to the water. How will they break up water? So in general, the rule of thumb is that cations can be either acidic or neutral, and the anions can be any of the above. So we can have an anion being acidic, basic, or neutral. So let's get into that. When we have, we're first going to talk about anions. So when we have anions of our strong acid, so let's say HCl. When HCl breaks apart, it forms hydrogen and chloride. So if I'm just dealing with something like chloride, now we know that hydrochloric acid is a strong acid, so the basicity of chloride is negligible, meaning it's not going to react with water to do anything. It's going to just sit in solution, right? It will never go backwards to create HCl. So when I have HCl plus water, no reaction happens. So that's saying that anions of strong acids are neutral. They're going to form neutral solutions because they're not going to react with water to form hydroxide because they're so weak, negligible. Anions of weak acids are conjugate bases, and so those are weak bases, right? Weak acids form weak bases, where strong acids or bases form negligible conjugates. So when we're dealing with something like acetate on its own, so let's say again like sodium acetate, when it reacts with water, acetate can only pick up a hydrogen, so we'll form acetic acid. And then what's left from the water is hydroxide. So when we have something that is a conjugate base, it's going to form a solution that's basic. So bases form basic solutions. When we're dealing with something like a polyprotic acid, it can either act like an acid or a base. So let's, for example, use something like sulfurous acid. So that's H2SO4. It can react with water to form HSO2 minus plus hydronium. Then that second hydrogen, so now our conjugate base here, can react with water. So this is what we're talking about. This conjugate base, what can it do? So it can either react with water to form, again, H3O plus and now sulfite. Or it could take this reaction and go backwards and pick up a hydrogen and become sulfurous acid. So we want to think about what is it going to do. So what we can do is, we know that this first one has Ka1, that's the strength of the first acid hydrogen coming off. Now we have Ka2. So we can compare how big this Ka is for this forward reaction here compared to this hydrogen sulfite going backwards. So we want to know the actually the Kb. So we're going to use this first Ka and we're going to flip it. So we're going to do 10 Kw, 10 to the negative 14, divided by our Ka1. And we're going to compare the Kb here, so this value compared to this second value. And whichever one is bigger means that the anion will be that solution. So if our Ka for this if our hydrogen sulfate has a bigger Ka than it does a Kb, then it's going to be acidic. If the Ka is less than the Kb, the anion will be basic. So basically, if it's more strongly acting like a base, like on the top one, then it's going to be basic. If it's more strongly acting like an acid, it will be acidic. So that's the gist of that. For cations, there are some general rules. So cations, right, are positively charged. So any group or 1 or 2, so the alkali or alkaline earth metals, they're always going to form neutral. They're never going to affect the acidity. When we have polyatomic cations, so something like ammonium, right, or they're the conjugate acids of our weak bases, when they react with water, they're going to form hydronium and the weak base. So they're going to just basically go backwards. So basically they're forming acids. And then our transition metals and post-transition metals, so this is group, the D group and the F group, right, those blocks, those are going to be acidic. And so that doesn't really make sense. Like, why would they be acidic? So let's talk about it. So with these transition and post-transition elements for these cations, they're going to form this hydrated complex. So hydrated means water, right, attached with water. So here's iron 3, and it is surrounded by waters, and this is what happens when any kind of metal is dissolved in water. But because this metal is so positively charged, it actually starts to pull pretty strongly on the oxygen from the hydrated water, which makes this bond between the oxygen and hydrogen in water weaker, and sometimes weak enough to where there's surrounding waters that aren't part of the hydrated complex, they can come and actually pick up a hydrogen and become hydronium. So when we have cations with a higher positive charge, they're going to be stronger acids and produce more hydronium. When they have a smaller charge, they're quite a bit weaker. So basically the metal is making the hydrated water acidic, able to donate a hydrogen into the free water molecules. So let's do some predicting. If we have a group 1 or 2 metal cation with an anion of a strong acid, so let's say like sodium chloride. So what we want to do is look at the sodium, realize it's a group 1 metal, so that's going to lead to a neutral solution. When we look at chloride, we know that it's the conjugate base of a strong acid, so it's also going to be neutral because it can't form any acid. So it can't go backwards to form HCl. So this is going to be a neutral solution, which makes sense. Like, we don't think of salt water as being acidic. When we have a group 1 or 2 metal, so let's say potassium, with the anion of a weak acid, so let's say acetate. So if I have potassium acetate and I put it in water, we want to look at potassium. It's a group 1 metal, so again it's going to be neutral. And then we look at acetate. It is a conjugate base of a weak acid, so it is a base, so it's going to lead to a basic solution. It's going to end up reacting with water to form hydroxide. So this is going to be basic. Now if we have a transition metal or a polyatomic cation, so that could be either ammonium or it could be something like iron or aluminum, metal, right? So let's say aluminum, with an anion of a strong acid, so let's say chloride. So I look at aluminum and I'm like, okay, well, that's a transition metal. It's +3 charge. That's going to lead to an acidic solution because the hydrated waters are going to be tightly pulled, leaving the hydrogens feeling a little weaker and being able to be pulled off by free waters. I look at chloride and say, okay, well, that's a conjugate base of HCl, and that's a strong acid, so it's not going to do anything, so the chloride's going to lead to a neutral solution, so we end up being acidic. When we have a post-transition metal, so again, transition metal or polyatomic cation, so in this case I'll use ammonium, but it could also work with something like iron or aluminum, with an anion of a weak acid. So let's say acetate again. So if I have ammonium acetate, what's going to happen? Well, we know that our weak acid here, so ammonium is going to lead to an acidic solution to form ammonia. And then our acetate, which is our weak base, is going to produce a basic solution. So what we have to do is compare the Ka of ammonium to the Kb of acetate and see which one is bigger. Whichever one is larger is going to let us know, is the solution with ammonium acetate going to be acidic or basic. In class we did a demo where I grabbed some salts and we tested it with litmus paper to see what the acidity was. Next, we're going to think about other factors that affect acid strength. So specifically we're thinking about the structure. So when we have an acid, so hydrogen conjugate base bond, okay, right, our acid bond, we are going to generally have the case that the element A here has a different electronegativity than hydrogen, right? So it's pulling the electrons in that bond, making hydrogen partially positive and making the element A partially negative. Now the bigger this difference, the bigger that electronegativity difference, the more polar the bond is, making it a weaker bond. So these weaker bonds are able to be broken more easily, so that the acid ends up being stronger the weaker that they're held together. Also, if our conjugate base, A-, happens to be a pretty stable anion, then that's going to be a stronger acid. So when we're dealing with things like chloride or bromide, right, these are group 7, they're halides, and now they have 8 valence electrons now that they're halides. they're very stable. They have reached the same kind of electron configuration as their closest noble gas, and this helps to keep them in that form, making them not want to share that electron. They want it all to themselves. So if a hydrogen is attached, they're having to share it with the electron with the hydrogen, and that's not very good for them. So let's think about these different salts and determine whether they're going to be acidic or basic. Take some time to do it on your own. Identify the cation, identify the anion, and what it will do with water to determine what's going to happen. Okay, hopefully you did that. Now we're just going to look at these. So barium is a group 2, and so that is going to be neutral. Let's put an N. Acetate here is the conjugate base, is a weak base, so that's going to lead to the solution, or acetate making the solution basic, forming hydroxide. So neutral plus basic means that number for A will be basic. Now we look at B, we have ammonium, that's a weak acid, so that's going to lead to it being acidic. Chloride's a conjugate base of a strong acid, so it's going to be neutral. So for B, ammonium chloride, it's going to be acidic. Here we have, you might be kind of freaked out by seeing this compound. This is methyl ammonia, so it's methylamines conjugate acid. So you should be familiar with it from the weak base table. It has the conjugate acid for methylamine, so it's this compound. So this is a weak acid, so this is going to lead to it being acidic. Bromide is the conjugate base of a strong acid, so leaving it neutral. So this one, C, will be acidic. Now we have potassium, group 1, so that will lead to neutral. Nitrate is the conjugate base of nitric acid, which is a strong acid, so this will also be neutral. So for D, this solution would be neutral pH. And then lastly, we have aluminum. Aluminum is a transition metal, so it's going to give us an acidic solution. Perchlorate is the conjugate base of a strong acid, so that will lead to it being neutral. So again, we're going to have a neutral solution. Now we're going to look at this salt. It's sodium biphosphate. So the sodium, again, is not going to do anything. So what we have here is hydrogen phosphate, and we want to see what is it going to do. So in both cases, it's going to react with water. So let's first think about what's going to happen if it acts like an acid. So if it acts like an acid, it's going to donate its hydrogen to be ammonium, and then a phosphate. Okay, so we're going to look. So we want to look at phosphoric acid. Now, losing its first hydrogen, that's our Ka1. So that would be phosphoric acid going to dihydrogen phosphate. We don't have that here right now. We don't have phosphoric acid anywhere in this equation. Then this next one would be dihydrogen phosphate, so H2PO4 going to HPO4 minus, or 2 minus. So we don't have that happening at this point. Then this third one would be hydrogen phosphate going to phosphate, and that is what we have. So this, we're going to use Ka3. So that is what is happening for that third hydrogen coming off. Now when we look at it acting like a base, we want to think about it gaining a hydrogen. So now it's going to become H2PO4 minus and hydroxide. So what do we have here? We have hydrogen phosphate and dihydrogen phosphate. And so that's our conjugate acid-base pair. So if we look at it written, that is with, if we look at it going backwards, the second hydrogen would come off to form hydrogen phosphate. And so this is a base reaction, so we can't compare Ka's for this reaction. It's not an acidic reaction. So what we want to do is think about K2. That would be if our dihydrogen phosphate formed hydrogen phosphate. But now it's the flip of that, so we want to think about this being Kb, but which Kb? So let's come down here for the Kb. We're using the second Ka, so we'll call it Kb, 2. And what we're going to do is use Kw relationship divided by Ka2 to get us the Kb2. So we're going to do 1 times 10 to the negative 14 divided by Ka2, which is 6.2 times 10 to the negative 8. So what we get here is our Kb for this reaction for our hydrogen phosphate acting like a base is 1.6 times 10 to the negative 7. So now we can compare Ka3, which is 4.2 times 10 to the negative 13, compared to this Kb, 1.6 times 10 to the negative 7. Well, the Kb is larger, so this solution is going to be basic. Now let's think about dipotassium, the dipotassium salt of citric acid, so that would be hydrogen citrate. So again, potassium is a group 1, we're not going to worry about it, we're just going to look and see about this hydrogen citrate acting like an acid, that should be a 7, and acting like a base. So hydrogen citrate. So here's an acid. Either way, they're both reacting with water, because that's what's going to happen when we dissolve them. They're going to be interacting with water, and some of them are going to be doing this acidic reaction, and some of them are going to be doing this basic reaction. So we have to see which one's more strongly pulling, which one is producing more hydrogen or hydroxide ions. So let's say when it's acting like an acid, we're going to take off that last hydrogen to make hydronium and citrate. And here it's going to be acting like a base, so it's going to be pulling off a hydrogen from water and producing dihydrogen citrate. So let's think about acid-base pairs here. So here is the last hydrogen coming off. So let's go to citric acid and find what the last hydrogen coming off is going to be. 4, so this is the Ka for that last hydrogen. Ka3 is 4 times 10 to the negative 7. Now we want to look at what's happening between this, now acting like a base, so this base forming this conjugate acid. So this is between the second hydrogen coming off to form the conjugate base. So we're going to use this Ka to find the Kb for the reverse reaction. So we have Kw over Ka2 equals Kb2, which is 1 times 10 to the negative 14 divided by the second Ka, 1.7 times 10 to the negative 5th. So what we get is 5.88 times 10 to the negative 10. So this this molecule acting like a base is weaker than that same molecule acting like an acid when we compare the Kas to the Kbs. So this solution is going to be acidic. We're going back now to structures, thinking about how structures affect acidity. So first we're going to talk about binary acids. So binary means 2, so we're specifically thinking about hydrogen bonded to only one other type of element. So that would be any kind of hydrogen plus like a halide or an oxide, sulfide, so on. So within a group, meaning down the column, we're going to think about the hydrogen A bond, so any of those other elements, for those, what's going to be most important is the strength of the bond. So when we're dealing with the group, we're talking about going down. So as we go down, we're getting weaker bonds. These molecules are getting bigger, the hydrogen's getting further away, so this bond is weaker. And we can see that with dihydrogen sulfide. It's a weak acid, and then this hydrogen selenium compound, its Ka is much bigger because the hydrogen and selenium are further away, so the bond is weaker, so it's easier to come off. We see that again with hydrofluoric acid, right? That's one of the reasons why that it isn't a strong acid. It's super electronegative, but the fact that the hydrogen and the fluorine are so close together, it can actually escape to form a strong acid. Within a period, so going across from left to right, the bond polarity is going to be the most important part. When we have a bond that's more polar, that's going to make it easier for the hydrogen to be removed, because basically the other element, the anion, is pulling harder on that electron, kind of stealing it more, so hydrogen can be more easily removed. It's not invested in the bond. So if you think about something like methane, the carbon-hydrogen bond, that's not very electronegative. They're sharing really equally. There's no reason for hydrogen to leave because it's being shared with. Now hydrofluoric acid, fluorine is much more electronegative, and so it is stealing the hydrogen a lot more, or the electron from the hydrogen, so hydrogen can come off a little bit easier. With oxyacids, these are acids that have a hydrogen, oxygen, and a nonmetal. So we're thinking about, any of those 8s and ites we've been talking about and how they make acids. So like sulfurous acid, sulfuric acid, any kind of ichorous acid, those are the oxyacids. So for this, we're thinking there's a couple things. So first thing is, as the electronegativity of the nonmetal goes up, okay, so as we go further to the right and up, we're going to get a increase in acidity. So when we're thinking about, here's a bunch of acids. So hypochlorous, hypobromous, hypoiodous, right? These are all weak acids. They're not the X, they're the S's. And so as we go up from iodide to hypobromous and hypochlorous, you can see that the strength of the acid goes up. That has to do with those electronegative atoms helping to weaken the hydrogen bond so it can be removed easier. If an element has more than one oxygen, so let's look at the chlorous, hypochlorous, chlorous, chloric, and perchloric, right? So all we're doing is adding and taking away oxygens. So the rule for this is the oxyacid with more oxygen atoms is going to be more acidic. So, and we see that, right? Hypochlorous is weaker than chlorous, which is weaker than our strong acids, chloric and perchloric. So the more oxygens there are, the more acidic. The last thing about learning that we're going to do is Lewis acids and bases. So with Arrhenius, we were talking about acids and bases having to do with increasing hydrogen concentration or hydroxide concentration. With Bronsted-Lowry, we're specifically talking about being hydrogen acceptors or donors. Right? And now we're still going to be thinking about accepting and donating, but we're specifically going to be thinking about accepting electron pairs or donating electron pairs. So in this case, Lewis acids are going to be acceptors of lone pairs, and Lewis bases are going to be donating our lone pairs. And we talked about that a little bit with Bronsted-Lowry. We talked about the hydrogen attaching to the lone pairs of a base. But now we're just being explicit about that is now the definition. And it helps that all Bronsted-Lowry acids and bases are also Lewis bases. It works out that way. But there are some compounds that are acidic or basic, but they don't meet the Bronsted-Lowry definition. So here is hydrogen attaching to ammonium. So this is, if we think about Bronsted-Lowry, hydrogen is being lost from an acid, right? And ammonium is acting like a base and accepting the hydrogen to form hydronium. So here we have acid going to base, right, to form our new compound. But in here we have this Lewis base, and the nitrogen has a lone pair, so it's going to be able to donate it. And now we have this boron trifluoride. Now we wouldn't normally think of boron trifluoride as being an acid, but because of the fact that is going to be able to have room to take on that lone pair from the nitrogen, it is considered an acid. And more relevantly, I think, than this like weird kind of compound reaction happening between ammonia and boron trifluoride is this Lewis acid base definition helps to explain our metal compounds being acidic, because water is now giving a lone pair that the metal can accept. And so water being a Lewis base here, and because it has the lone pairs that it can donate, our metal being the acid, accepting those lone pairs, and then due to that, hydrogen can come off from surrounding water, or from this water molecule. So it's kind of like, due to the fact that the metals can bond to water, in turn makes an acidic solution. So in this case, the higher the charge of our metals makes it a stronger acid, because it's being pulled tighter, the water is being pulled tighter to the metal, making those hydrogens loosely held, and so the surrounding waters can pull off more hydrogens the higher the metal charge is. So the last thing we're going to do is going to compare the these different molecules and order them in terms of increasing strength. So first thing you want to do is identify the non-hydrogen things. These are all binaries right here. And so if we look at them, you can see that they're actually all on row 4 of the periodic table. So we can see that all of these other elements attached to hydrogen are in the same row, and from the rules, bond polarity is the most important part there. So we could look and say, okay, which is the least polar of the bonds, and that's going to be potassium and hydrogen. So the larger the polarity, the stronger the acid. So something on the right side of the periodic table is going to be stronger than the left. So in order of that, we have potassium hydride. Then we have this ASH3. I actually don't know what it's called. Then we have this hydrogen selenium compound, and then very lastly, closest to the right, is hydrobromic acid. And we do consider that a strong acid, so it lines up. And we don't consider a hydride, which is where hydrogen has a negative charge here, because the potassium is a positive charge. We don't even consider that an acid. We consider that a base. So this makes sense. Now for the B, what we want to think about, here we have these polyatomics, these oxyacids. So for oxyacids, first thing is we want to look at is the nonmetal, which one's going, because we have selenium versus sulfur. So for this case, the higher the electronegativity for oxyacids means that it's going to be more acidic. So sulfur is higher, right? Is right above selenium. So sulfuric acid is going to be the strongest. Then when we are comparing seleniums, the one with more oxygens is going to be the stronger than the less oxygen. So we're going to have this compound. And then lastly, our weakest will be the one with only 3 oxygens. In this last example that we're going to do in this chapter, we're choosing in each pair, choose the one that's more acidic. And so here we have 2, so other than the rules that we know, just thinking about the trends, we have 2 binaries. So the rule for binary, these are right above and below, they're in the same column. So we want to think about which bond is going to be weaker. So since fluoride is closer to the hydrogen, right, they're smaller molecules together, that bond is stronger. So hydrobromic acid is stronger than hydrofluoric, which we already know. For B, we want to look at phosphine and sulfur, or phosphorus and sulfur. They are in the same row. So with that, we're not thinking about bond strength so much as bond polarity. So which one is more polar? Well, we know that sulfur is closer to the right, so with increasing polarity. And so that one's going to be more acidic, and we can verify based on the Ka. Now, nitrous versus nitric acid. With these acids, we want to look at the one that has most hydrogen, is most acidic, so nitric acid. And then with the oxy acids here, we have sulfurous and selenium acid. And they have the same number of oxygens, so we're going to be looking at the electronegativity, seeing which one's more electronegative. Well, sulfur is higher up, and so it has higher electronegativity, so sulfurous acid is stronger. This is it. We are done with this really long chapter, and I'm hoping that this last section with minimal math was a little bit more mellow for you to understand.